right, good morning and welcome back to microprocessor course. Today's class we are going to finish up the memory management techniques that we started last class. Then we're gonna start the class about input-output devices. So we have seen that even though the main purpose of this course is microprocessor, because it doesn't work alone, we have seen the memory system. So it's a good idea if we can also have a brief introduction about the interaction with microprocessor and the input-output devices. So we're gonna learn the last memory management technique, the virtual memory. Then we started the input-output devices, which focus more on the interaction between microprocessor and input-output devices. So before we start today's class, I'm gonna check if everybody is present in today's class. 5 number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 6 number 1, 2, 3, 4, 5, 6 number 5, 6, 6 number 6, 7, 6 number 7, class 6 number 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 22, 23, 24, 26, 27, 28, 29, 30, B21, 15. Okay. All right, so we're going to finish up the memory management technique lecture that we started the last class. We talked about the swapping, which is a memory management technique which temporarily moves the entire process between the random and the disk to free the memory. Now, we also talked about the paging, which is another memory management techniques, which has to divide the memory into fixed site blocks that we call frames, and we have each process that needed to be divided into fixed size blocks that we call pages. And the page needs to be loaded into a specific frame into the main memory. So today's class, we're gonna extend the memory management technique to see the virtual memory, which has to extend the random access memory using the disk storage, external memory. So a short review, we have seen that the effective memory management is very important, especially in a multi-programming system, because there are some processes that are not in ready state, which keep the central processing unit in idle state, waiting for them to get input from the input-output devices. So if only we have a few number of processes which are loaded into the main memory, most of them, they'll be waiting for the input-output. So during this time, we have the central processing unit, which remains idle, and it has to reduce as a result, the overall system efficiency. We have seen that we have processes which are in a long-term queue, and we have other processes which are in term queue, short-term queue. Those processes in long-term queue need to be moved to the short-term queue as long as we have a space which is available. Then the processes from the short-term queue need to be moved to the random access memory to be executed by the processor. Then we have job requests which enter the long-term queue as long as the internal resource becomes ready. Now, we talked about the swapping, which moved out the processes from the random access memory to the disk, especially in the intermediate queue, and bring new processes from the disk or from the intermediate queue to the random access memory, because most of the processes in the random access memory are not in ready state, which has a big impact on the computer system, because it's going to have more processes which are in ready state to minimize the long waiting time for the central processing unit. So with the simple job scheduling, we have processes that need to be moved from the long-term queue from the disk storage to the random access memory as long as we have a space there. Then we have completed the job that needed to be moved out from the random access memory to get free space for the new processes. Then, because if we have a big number of processes in the random access memory which are not in ready state, we have the central processing unit which needed to be in a long waiting time. So to solve each issue, we have the swapping method. You see, if the processor found out a big number of the processes are not in ready state, those processes are needed to be moved out, swapped out from the random access memory to the disk storage, either into the intermediate queue, then bring new processes from the intermediate queue or from the long-term queue. Then the processor will have more processes which are in ready state. And as for the simple job scheduling, we have completed the jobs that needed to be moved out from the random access memory to get a free space from new processes. Now, with unequal fixed size and variable size partitions, we have inefficiency in memory management. So to solve this issue, paging allows the memory to be divided into equal but small fixed size chunks that we call frames, and we have the processes that are divided into small fixed size chunks that we call pages. And we have pages that are assigned to available frames into the main memory. Now, we have to maximize the space usage, storage space usage, and only with the paging, the only last page needed to be wasted. So this will solve the issue of wasting of the storage space. Now, we have discussed about the paging. We see that we have a process A, which has a number of pages. We have a process A. Then for the process A, we have a number of pages. We have page 0. We have page 1. We have page 2. Then we have page 3. Whenever a process is loaded into the main memory, we have a page table which is created. Now, if this process A is loaded into the main memory, we have a page table A which is loaded. Page table A load, which is created to hold the mappings between the pages and the frame. Now imagine we have another process B. Which include also a number of pages, page 0, page 1, page 2, then page 3. If this process is loaded into the main memory, we have a page table which is created to hold the mappings between the pages and the frame, page table B, and so on and so forth. Now, for example, here we have the main memory which is divided into a number of frames, and we have seen that these pages from this process A needed to be loaded into the frames which are available into the main memory. Now we have seen that the page 0 is loaded into the page frame number 18, and we have the page 1 which is loaded into the frame number 13, and so on and so forth. So we see that now we have the page table for the process A which is created, and it includes the frame numbers 18, 13, 14, and 15. So this way you see that whenever a process is loaded into the main memory, we have a page table which is created for the process. Now, it is very important to know that we need the system to do the logical and the physical address translation. Now, with the page number, we have the page number and the relative address within the page that we also call offset. We have the logical address. That means that the logical address is equals to logical address is equals to the page number plus the relative address within the page. We call it also offset. For example, we have the page number 1 and relative address within the page which is 30. That is, the logical address is 130. Now, with the physical address, because we have each page number that needs to be loaded into the main memory into a specific frame, to get the physical address mapped to this logical address, we have the frame number in which the page number is loaded. We have the page number 1, which is loaded into frame number 13, and then we have the relative address within the frame, which is 30. Then we can get the physical address for the logical address. Now, physical address equals to the frame number. We have a frame number plus relative address within the frame, this time within the frame, not the page. We call it also the offset. Now here we can get easily the translation between the logical address to the physical address by using the frame number and relative address within the frame. Now, processor use page number as well as relative address and the page table to get the physical address of a logical address. Main memory is divided into frame, and the processes are divided into pages. This is something that we have seen. So small processes have few pages, and bigger processes have more pages. So whenever a process is loaded into the main memory, we have its page table go into the available frame, and a page table is created to hold the mapping between the pages and the frame. So this way you see for each process that is loaded into the main memory, we have a page table which is created for the specific process. Now, we needed to understand that paging can help to speed up the processor execution, but it is limited. We needed to know that the main memory size is limited. Therefore, we can't load all the processes into the main memory at once. So to solve this issue, virtual memory is there to extend in some ways the random access memory to seems to be bigger as it is physically. So this allows more processes to be loaded into the available memory. So demanding paging load the page into the memory, and it has to be loaded only when they are needed and when we have free space for them. So we have programs which typically use a small portion of code or the data at a time, which demonstrate the principle of locality that we have seen. Now, a page fault happens when a program is trying to access a page which is not available into the main memory. That means the system will expand the page request into the next level of the memory hierarchy, which is the external disk, external memory. Now, we have only a few number of pages per process which are kept into the memory, which allow more processes to run efficiently. So we have the operating system that needed to remove page to get a new a free space into the main memory using what we call page replacement policy, as we have seen for the cache memory. When the cache is full and the system needed to load more blocks from the main memory, we have the system that needed to use what we call replacement policies, cache memory replacement policies, to get a free space for new blocks from the main memory. Now, we're going to start with the virtual memory. We have seen that the random access memory has a limited size, so that means we can't load all the processes that we have at once. Demanding page avoid loading the entire process into the main memory, but we have seen that the processes can exceed the physical memory size. So to solve this issue, we have programmers that no longer need to manually split the large program. Instead, we have the operating system and the hardware that needed to handle the memory and make it appear bigger. So we have to use the disk allocated memory, and it has to seem as a virtual memory, which has to support multi-programming. Now, we have seen that for each process that is loaded into the main memory, there is a page table that needed to be created to hold the mapping between the pages and the frames, because we have seen that each page needs to be loaded into a specific frame into the main memory. So we have memory accesses that require the translation of the virtual address, the logical address, which consists of the page number and the relative address within the page, to the physical address, which consists of the frame number as well as the relative address within the frame. So a virtual address which consists of a page number and an offset needed to be translated to a physical address which consists of a frame number as well as the offset. So the translation, address translation is performed using the page table that has to be created when a process needed to be loaded into the main memory. Now, page tables are there to be stored in the main memory due to their big size. We have all the page tables for the processes that need to be stored into the main memory because they have a big size. Now, page table structure. We have seen this picture, which allows the pages from a process to be loaded into the main memory. And we have seen how the translation between the logical address to the physical address has been done. Now, this is a process which includes a number of pages. Now, a specific page from the process needed to be loaded into a specific frame into the main memory. This is the example that we have here on the screen. We have page number 1, which needs to be loaded into the frame number 13. And this page has a relative address which is 30. Now, we have this logical address which consists of page number as well as the relative address. We need is a translation to the physical address, which is the frame number in which the page number is loaded into, and the relative address within the frame. Then we get 1330 as the physical address, which is mapped to the logical address for this specific page. Now, most systems have one page table per each process. For example, we have the VAX, which have up to 2 gigabytes of the virtual memory. We have a virtual memory size for the system, VAX system has virtual memory size equals to 2 gigabytes. We have the page size equals to 512 bytes. To the power of 2 gigabytes equals to the power of, hello, 2 gigabytes is what? Kilobyte? KB? Megabytes? MB? Gigabyte? Hello? Tell me. KB is 2 to the power of, 10, yes. 2 to the power of 10 bytes. Megabyte? 20. Gigabyte? 30. Then we have 2 to the power of 30 bytes, which is equals to 2 to the power of 1 times 2 to the power of 30 bytes equals 2 to the power of 31 bytes. Then we have a page size of 512 bytes, that is 2 to the power of 9 bytes. Then since we have the virtual memory size, we can get the page table entry, page table entries equals to the VM size divided by the page size. We have 2 to the power of 31 divided by 2 to the power of 9. Then we have 2 to the power of 22 entries. Page entries. So see how many entries each page table has. And we know that we have thousands or millions of processes. So that means each process that needs to be loaded into the main memory, we need a page table that needs to hold the mappings between the pages and the frames. So we have these pages that need to be stored into the main memory because of their bigger size. So we have larger pages table which needed to use a lot of memory. So they are often stored in the virtual memory and paged like regular pages. At least we have a part of the page table, including the entry for the currently executing page that has to remain into the main memory. So we have the big page table that often take a lot of memory. So we have them to be stored into the virtual memory, and they paged like a regular page. Now, because we have each page table that needed to be created for each process that is loaded into the main memory, and we have seen that the page table includes a big number of entries, so they are stored into the main memory or into the virtual memory. But because we have a big number of processes, we needed to think about how we can save a bit space or storage space. That's why we have this inverted page table to solve the issue of wasting space for the page table. Inverted page table are an alternative to one or two level page table, and it has to be used in a very important powerful computer system like the Power PC or Illustra Spark. So we have virtual pages which are mapped to what we call hash vary, and the hash vary needed to point to the page table with one entry per little memory frame. So this will help to solve a bit the waste of the storage space. Then we have chaining that need to handle collision with chains which usually have one or two entries. So we call inverted page table because we have entries which are indexed by the frame number. We have entries which are indexed by the frame number instead of virtual page number. Now here we have inverted page table structure. We have the virtual address which include the page number, and we have the offset. All form a number of n bits, and this virtual address needs to be passed by a hash function, then we get m bits. Now you can see here that we have the inverted page table which include the processor ID as well as the virtual page. And each inverted page table has at least one entry for each physical memory frame. We have inverted page table. Here we have inverted page table which include one entry for each physical memory frame. Then we can get easily the physical address which is mapped to this virtual address. So this way we have the inverted page table which only include one entry for each physical memory frame. Clear? Clear? Are you there? Huh? Are you there? Huh? So we have inverted the page table, which include only one entry for each physical memory frame. You see we have the virtual address, which include the page number, as well as the address, relative address within the page that we call also the offset. Then it has to be passed by the hash function to get m bit, and we see that for the entire system we have a virtual, the physical frame which include the PID, that is the process ID, as well as the virtual address, the virtual page, and each inverted page table include only one entry for each physical memory frame. We can get easily the translation of the virtual address to this real address, the physical address, which is now m-bit, which include the frame number as well as the relative address within the frame, which also we call also offset. Okay, now, if you still remember, when we talked about the cache memory, we have seen that the cache memory is there to solve the issue of having the central processing unit to go through the main memory multiple times. So it acts as a buffer between the central processing unit and the main memory. Now, since we have each process that needed to have a big number of tables, and those tables need to be loaded into the main memory, and we have each virtual memory reference which require at least 2 physical memory accesses. One is for the page table entry, another one it is for the data itself. These will have to double the memory access time in a straightforward virtual memory system. Now, we have most of the virtual memory system which use a special memory cache for the page table entry that we call TLB, Translation Look Aside Buffer. Translation Look Aside Buffer, TLB. Now, the translation look aside buffer function like a cache memory, and it is there to store the most recently page table entries. Hello? What is the main purpose of the cache memory in the computer system? What is the main purpose? Now, here you see the translation look aside buffer. It acts as the memory cache, but it is there to store the most recently used page table entries. Now tell me, we talked about the cache memory. What is the purpose of the cache memory? What does the cache memory store? What type of data does the cache memory store? This translation look aside buffer stores what we call most recently used page table entries to avoid the system to go to the main memory multiple times. So same goes for the cache memory. We have the cache memory, which is there to store the most recently used data to avoid multiple accesses of the central processing unit to the main memory. So we have this translation look aside buffer to store the most recently used page table entries to avoid the central processing unit to go through the main memory many times. Now, by the principle of locality that we have learned, we have most of the references that are to the recently used pages. How does the page translation look aside the buffer works? We have the central processing unit, which needed to check for the page table entry into the translation look aside the buffer. Okay. Now, if the page table is in the translation look aside the buffer, we have a TLB hit. Then the central processing unit will generate a physical address for the page. Now, if the page is not available into the translation look aside the buffer, we have the system which expanded the request of the page entry into the main memory. Now, we have two different scenarios. If the page table entry is available into the main memory, we have the translation look aside buffer which needs to be updated. Then the central processing unit will generate a physical memory for the page. If the page table entry is not available into the main memory, that is the second scenario. We call it a page fault. Then this is gonna take a longer time, because the operating system needed to instruct the central processing unit to read the page from the disk. The central processing unit, we have to activate the input-output hardware. Then we have the page that needed to be transferred, to be transmitted from the disk to the main memory. That is the upper level into the memory hierarchy. Now we have two different scenarios. We needed to check the status of the memory, the random access memory, the main memory. Is it full or not? If the main memory is full, page replacement policy needs to be applied to get a free space for the page entry, for the page table. If the main memory is not full, we need the page table to be updated. Then that is the end of the operation of the paging as well as the translation look-aside buffer. Is this clear? Hello? Is this clear? Great. Now, we have page table entry. Page table entry available into the TLB, TLB translation look-aside buffer. If it is available page table entry, is it available into the TLB? Yes or no? If it is yes, if we have this page table entry available into the TLB, we have a TLB hit, right? Now, if the page table entry, page table entry available into the TLB, not available into TLB. We have TLB miss. Then once we have got the TLB miss, we have two different scenarios. So is the page table available into the main memory? Available in main memory, yes. Yes, then if it is available into the main memory, we have the TLB updated. The action is update TLB. Update TLB, translation look-aside buffer. Now, the second scenario here is in main memory. No. If it's not in the main memory, we have what we call a page fault. Main memory. Then we have what we call a page fault. That means this is the worst scenario when the page table needs to be loaded from the external memory, the disk, to the main memory. So when it's not available into the main memory, the operating system needed to instruct the central processing unit to read the page table from the disk. Then the central processing unit, we have to activate the input-output hardware. Then we have a page table that needed to be transmitted from the disk to the main memory. But we needed to check the status of the main memory. Is the main memory full or not? If the main memory is not full, we have the page tables that needed to be updated. If the main memory is full, we have the system needed to perform what we call a page replacement policies. Then we can get the page table updated into the main memory. Is this clear? Huh? Hello? Is this diagram clear? Huh? So this operation of paging and translation look-aside buffer is similar to the cache memory. For the cache memory here, cache memory. If a block is available into the cache, we call it hit, right? Available into the cache. Yes, available in the cache. Yes, that is a hit. A block of data not available into the cache memory. Block not available into the cache memory. Cache memory. We have a miss. Not available into the cache memory. We have a miss. All right, so we're gonna continue with the TLB and the cache operation. The virtual memory system has to interact with the main memory, cache memory, as well as the translation look-aside buffer. So we have the virtual addresses which include the page number as well as the relative address within the page, that is the offset. Then the memory system, we have to first check the TLB to see if the page table entry is present there or not. If the page table entry is found into the TLB, we have the physical address that needs to be generated by combining the frame number with the offset. If the page table entry is not available into the TLB, we have the page table entry that needs to be retrieved from the page table into the main memory. Here we have the TLB operation. We have the virtual address, which include the page number as well as the offset. Then we have the system that needed to check if the page table entry is available in the translation look-aside buffer. If it is available there, we have a TLB hit, and we have the address, the physical address, which is generated by combining the frame number as well as the offset. Now, if the page table entry is not available in the translation look-aside buffer, we have a TLB miss. Then the system will expand the page table entry into the main memory, which is the next level of the memory in the memory hierarchy. Then if it is there, we have the TLB that needed to be updated. And you see for each process, we have a page table. Here we have the read address. Here in the cache memory, we have the read address, which include the tag here, and the reminder here is for the line number or set number, depending on which kind of the cache mapping technique which has been to use. And we have here the cache memory. If the block is available in the cache memory, we have a hit, and the value will be returned to the system. Will be returned to the central processing unit. If the block of the data is not available there, we have a miss. and the request of the block of the data need to be expanded to the next level into the main memory, which is the next level of the memory in the memory hierarchy. Questions? So this is your 5-minute break. You take your break. We're going to resume class after break time.